Good morning, students. This is Max class, and today we are going to learn the basic algebraic properties of complex numbers. Before going to that, we have to complete two problems. First, we will complete that and we will learn the basic algebraic properties. See here, example 2.2. Find the values of the real numbers x and y if the complex numbers 2 plus I into x plus 1 minus I into y plus 2i minus 3 and x plus minus 1 plus 2i into y plus 1 plus I are equal. Two complex numbers they have given that they are equal. We need to find out x and y. See, we have learned that if z1 is equal to z2, then real part of z1 will be equal to real part of z2 and imaginary part of z1 will be equal to imaginary part of z2. Is that clear? Okay, so first we will take the two complex numbers as z1 and z2. Then we can equate the real part. Okay, so we are going to take, let z1 is equal to 2 plus I into x plus 1 minus I into y plus 2i minus 3. Actually, I and imaginary part, real part, imaginary part, real part, all together it is mixed. So, we will separate first what is real part and what are the imaginary part. See, multiplied 2x plus ix plus y minus I into y plus 2i minus 3. So, I am going to separate the real part. That means without I. This is 2x plus y minus 3. Now, plus I into, take the imaginary parts, x minus y plus 2. Okay. So, I am giving it as equation number 1. Then z2 is equal to x plus minus 1 plus 2i into y plus 1 plus I. This also we will separate the real and imaginary part. X minus y plus 2y into I plus 1 plus I. Now the real part, x minus y plus 1 plus I into, here 2y, there are no coefficient means it is understood that is 1. This is equation number 2. So now you can write that is given z1 is equal to z2. Therefore we know that real and imaginary parts will be equal. So you can write equating the real and imaginary parts. See here the real part, 2x plus y minus 3 is equal to x minus y plus 1. Okay, now we can simplify, bring it into an equation. The next we can equate the imaginary part. See 2x plus y minus x minus y when it comes to this side plus y equal to, here we have 1, this minus 3 when it comes to the next side it will become plus 3. 2x minus x is x plus y is plus 2y is equal to 4. This is our new equation, equation number 3. Now we can equate the imaginary part. See, x minus y plus 2 is equal to 2y plus 1. This also we can simplify. X minus y, bring the 2y here, minus 2y is equal to 1 plus 2 when it comes to the next side, minus 2. So, we may get x minus 3y is equal to minus 1. This is the next equation, equation number 4. Now, we have to solve equation 3 and 4. See, equation 3 we got it, x plus 2y is equal to 4. Now, equation 4 is x minus 3y is equal to minus 1. Shall we add it? Add or subtract? See, both same symbol, so we have to subtract. Here plus means it will become minus. Minus, it will become plus. Minus will become plus. X minus x will get cancelled. 2y plus 3y. 5y is equal to 4 plus 1 is 5. Now y is equal to 5 by 5. So we have got it. Y is equal to 1. Now substitute y is equal to 1 in equation number 3. Equation 3 says that x plus 2y, the value of y is 1 equal to 4. So x plus 2 is equal to 4. So we may get x is equal to 4 plus 2 when it comes to an x side minus 2. So we are getting x equal to 4 minus 2 is 2. This is ordinary calculation, isn't it? The question is find the real values of x and y when the given two complex numbers are equal. Shall we do one more problem in this? That's from exercise 2.2. Okay, exercise 2.2, third problem. Find the values of the real numbers x and y if the complex numbers 3 minus I into x minus 2 minus I into y plus 2i plus 5 and 2x plus minus 1 plus 2i into y plus 3 plus 2i are equal. Same like the example. If these two complex numbers are equal, we should find out what is the real numbers x and y. So as we did, first complex number we can take it as Z1 and the second complex number as Z2. So let Z1 is equal to. So first we have to simplify, isn't it? So shall we multiply? That is 3x minus I into x. Here minus 2 into y. So minus 2y minus into minus plus iy plus 2i plus 5. Now we have to separate the real part. Real part means without the I term, isn't it? This is 3x minus 2y plus 5 plus I into, here we have minus x plus y plus 2. So this is the first term. Now Z2 is equal to 2x plus minus 1 plus 2i into y plus 3 plus 2i. This also we can simplify first. 2x plus minus y plus 2y into I plus 3 plus 2i. Shall we separate the real part? Here we will be getting 2x minus y plus 3 plus I into imaginary part 2y plus 2. Is that clear? Now what we should do? Equate the real and imaginary part. So what is that real part there? 3x minus 2y plus 5 equal to, in Z2 the real part is 2x minus y plus 3. So we can bring it into a single term. 3x minus 2y, bring the 2x here, it will become minus 2x plus y equal to 3. This plus 5 when it comes to next side, that is minus 5. 3x minus 2x, x minus 2y plus y, that is minus y. 3 minus 5 is minus 2. I am marking it as equation number 1. Then imaginary part, there minus x plus y plus 2 is equal to, this is 2y plus 2. So minus x plus y, bring that here, minus 2y is equal to 2. This plus 2 when it comes to next side, minus 2. So we may get minus x minus y is equal to 0. Or which implies x plus y is equal to 0. So we can mark it as equation number Now solving equation 1 and 2, we should find what is x and y. So I am going to write the first equation, x minus y is equal to minus 2. The second equation is x plus y is equal to 0. See, if you need to cancel x, same symbol, subtract it. If you add, automatically y will get cancelled. See, opposite symbol. So we can add x plus x, 2x, minus y plus y will get cancelled. Here, minus 2. So x is equal to minus 2 divided by 2. So we may get which is equal to minus 1. Now what we can do? Substitute x equal to minus 1 in equation number 1. Equation 1 implies x minus y, isn't it? X minus y is equal to minus 2. The value of x is minus 1, minus y is equal to minus 2. Or minus y is equal to minus 2, minus 1 when it comes to next side, plus 1. So minus y is equal to minus 1. Both minus and minus will get cancelled. We will be getting y is equal to 1. So for this problem, the answer is x equal to minus 1 and y is equal to 1. So if two complex numbers are given and that is equal, we will be able to able to equate the real part and imaginary part, and we can find out the unknowns. Is that clear? By this, the second exercise is completed. Now the next part is we need to learn the basic algebraic properties of complex numbers. See, basic properties of complex numbers. Properties. Say addition, they have given in tabular column in addition and multiplication. Closure property. For any two complex numbers z1 and z2, the sum z1 plus z2 is also a complex number. When we add two complex number, again we will get a complex number only. The same way, when we multiply two complex numbers, the product z1 z2 is also a complex number. That we knew, isn't it? Second one is commutative. We know that in such chapter we might have learned A union B is equal to B union A, or A intersection B equal to B intersection A. Here in addition, commutative means what is the meaning? Z1 plus Z2 is equal to Z2 plus Z1. Multiplication, Z1 into Z2 is equal to Z2 into Z1. Is that clear? Now associative property also we know. For addition we have learned. Here also for three complex numbers Z1, Z2 and Z3, Z1 plus Z2 plus Z3 will be equal to Z1 plus Z2 plus Z3. If it is for multiplication, we know Z1, Z2 into Z3 is equal to Z1 into Z2, Z3. This is what we have learned. See, additive identity. There exists a complex number 0, that 0 can be written as 0 plus 0 into I, such that for every complex number z plus 0 equal to 0 plus z equal to z. This is what additive identity. When we add a number with anyone, we should get the same number. 5 plus 0 equal to 0 plus 5 equal to 5, isn't it? So for addition, in general, for addition, 0 is the additive identity. See, for complex number, 0 means 0 plus 0 into I is known as the additive identity. When we add 0 with any number, we will get the same number. That's why this is additive identity. See, for multiplicative identity, 1. So when we multiply with 1, we will get the same number, isn't it? See, there exists a complex number 1. 1 can be written as 1 plus 0 into I, such that for every complex number z into 1 equal to 1 into z equal to z. The complex number 1 equal to 1 plus 0i is known as the multiplicative identity. So the multiplicative identity is 1 and the additive identity is 0. For every complex number z, now additive inverse, there exists a complex number minus z, such that z plus minus z equal to minus z plus z is equal to 0. So there we got the identity 0, isn't it? Here we should get the answer equal to 0. So we know that for 2, the additive inverse is minus 2. Already we have learned in the lower classes. The same thing. Even in matrices we might have learned the additive inverse of A is minus A. The same thing here. The additive inverse of Z is minus Z. See here, minus Z is called the additive inverse of Z. Now the multiplicative inverse. For any non-zero complex number Z, there exists a complex number W such that Z into W equal to W into Z equal to 1. So W is called the multiplicative inverse of Z, and we will denote it as Z inverse, Z power minus 1. Now we will find it out. Okay, we have a property that what is Z inverse. Now distributive property. For any three complex number Z1, Z2 and Z3, Z1 into Z2 plus Z3 is equal to Z1, Z2 plus Z2, Z3. Just multiply it. And Z1 plus Z2 into Z3 means what we will get Z1 into Z3 plus Z2 into Z3. Property. For any two complex numbers Z1 and Z2, we have Z1 plus Z2 is equal to Z2 plus Z1. See this properties till what I explained in the book, and this one it is you no need to write it, but from the next property onwards you have to write it. Okay. See the next one is, they have asked us like a question. Prove that prove that the multiplicative inverse of a non-zero complex number Z is equal to X plus IY is X by X square plus Y square plus I into minus Y by X square plus Y square. This we need to prove. So inverse, say proof, I am taking let Z inverse is equal to U plus IV be the inverse of Z is equal to X plus IY. We have taken, we don't know, no? Now we should prove Z inverse is equal to X by X square plus Y square plus I into minus Y by X square plus Y square. Okay, so I have taken let Z inverse is equal to U plus IV be the inverse of Z equal to X plus IY. Now we need to find out what is U and what is V. See, we have in that inverse property, we learned that multiplicative inverse, we know that Z into Z inverse is equal to 1. Z into Z inverse is equal to 1. That we knew it. Now shall we multiply it? That is U plus IV into or X plus IY into U plus IV is equal to 1. See, either you can ordinary multiply or even you can write it directly. That yesterday we learned in one like a formula, but it's easy for you. See, real part means we know that X and U is a real part, isn't it? When you multiply these two, we will be getting a real part. Then I into I, we know that is minus 1. So minus Y into V. Simple only, no, that's the real part. X into U. This simple you check it, plus into plus is plus, but I into I is I square, Y into V. The other two parts will be imaginary part only, plus I into X into IV means only V, that's imaginary part, isn't it? So X into V plus this Y into U. Is that clear? Equal to, this is 1. When we write it as a complex number, we may get 1 plus 0 into I. Suppose if you are finding much difficult to write this, multiply ordinarily. No issue. See, x into u plus I y into u. Multiply with this. Plus I into xv plus into plus plus I into I square y into v is equal to 1 plus 0I. Now xu plus I am taking this I outside. This is y into u plus x into v. I square, the value is minus 1. So minus y into v is equal to 1 plus 0I. I am writing together the real part, x into u minus y into v plus I into yu plus xv is equal to 1 plus 0I. When two complex numbers are equal, we know that real part will be equal and imaginary part will be equal. So, equating the real and imaginary part. See, x into u minus y into v is equal to 1. This is equation number 1. The next, y into u plus x into v is equal to 0. This is equation number 2. See why I have written u first? Because we need to find out u and v only. Okay. See, you can multiply and solve it and find out using this elimination method, what we did in the previous problem. If you have to eliminate u, what we should do? Here this first equation must be multiplied by y and the second equation must be multiplied by x, isn't it? Or we know that cross multiplication method. Are you remembering? Cross multiplication method. Using that also you can find out either this elimination method or by using cross multiplication method. If you are using this cross multiplication method, this constant term should be written in the left side. So I am writing, it will become xu minus y into v is equal to minus 1. Sorry, minus 1 is equal to 0. xu minus yv, this plus 1 when it comes to next side, minus 1 equal to 0. Here there is no coefficient, sorry, no constant term. Now when we write, we need to find out u and v. So I am writing uv constant. Let me write the equations. xu minus yv minus 1 equal to 0. The next equation is yu plus xv is equal to 0. These are the two equations. When we write here, how we have to write ma? We will be writing from the second term. Say minus y minus 1, then x again minus y. Then for the second equation, start from the second term. X 0, constant term is not there. Again y, x. Then we will put the arrow mark. U divided by minus y into 0 is 0 minus the next arrow, x into minus 1 is minus x equal to v by minus 1 into y minus 0 into x is 0, which is equal to 1 by x into x square minus y into minus y is minus y square, or u by x equal to v by minus y is equal to 1 by, see, x square minus into minus plus y square. Now shall we equate with the constant term? Sorry, u by x is equal to 1 by x square plus y square implies u is equal to x divided by x square plus y square. The same way, v by minus y is equal to 1 by x square plus y square implies v is equal to minus y by x square plus y square. Is that clear? Now we can write. Therefore, Z inverse u plus iv is equal to u x by x square plus y square plus I into v minus y by x square plus y square. So this is what they have asked us to prove. For ordinary numbers also, when they give, it is easy for us to find out. Say for example, if z is equal to 2 plus 3i, maybe find multiplicative inverse. Okay, find multiplicative inverse. Multiplicative inverse. So that is z inverse, isn't it? Z inverse, first value 2 by 2 square plus 3 square plus I into minus the second value by 2 square plus 3 square. It's easy to find out, isn't it? No need to find out any other thing. We can use this formula. Then we have to simplify. Maybe 2 by 4 plus 3 square is 9. Plus into minus is minus. I into 3 by 4 plus 9. Maybe 2 by 13 minus I into 3 by 13. Actually, in this exercise, we don't have any example problem. Like these problems only they have asked. Here, values will be given. Find additive inverse. Additive inverse for z, the additive inverse is minus z. For z, the multiplicative inverse is z inverse. Z inverse also, we have a nice formula. We have just proved z inverse is equal to x by x square plus y square plus I into minus y by x square plus y square. Is that clear? This proof you have to write it in the note. Other properties it is not necessary. Okay. Like our other algebraic sums, these complex numbers also obey the law of indices. What is that law of indices? Anyone? See, z power m into z power n is equal to z power m plus n. Okay, this is one. And second, see, z power m by z power n can be written as z power m minus n, like our ordinary algebra. Z power m, the whole power n can be written as z power m into n. Again, z1 into z2, the whole power m is equal to z1 power m into z2 power m. This is our ordinary algebraic indices. The same thing, complex numbers also obey the law of indices. Is that clear? So in the next class, we will do the sums from exercise 2.3. Be safe. Thank you. See you in the next class. Bye-bye.